Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the fourth lecture. This is the part B of the fourth lecture actually. My name is Engineer Jaffar and I'm instructor for this course. Let's start with the recapitulation of the previous lecture. In the last lecture we have discussed about an electric circuit, specifically op-amp, that is operational amplifier. We have looked at its types, that is inverted operational amplifier, and we have also derived the formula for that transfer function. Actually we have derived the formula for the transfer function of inverting op-amp circuit, and we have also done a numerical on it. Similarly, we have done another type of op-amp, that is known as non-inverting operational amplifier circuit, and we also looked at the derivation of the formula for the transfer function of non-inverting operational amplifier circuit. And in the last of the lecture we also did a numerical example to find the transfer function of a non-inverting operational amplifier. uh, we searched about Z1 Z2, and later on we inserted the values of Z1 and Z2 into the formula for both of these cases, that is inverted operational amplifier and non-inverting op-amp. So that was for electrical network. Now we will move towards, as you know, that we are moving towards mechanical network systems. And in the last of this mechanical, in the end of actually this mechanical system, we will combine the electrical systems with the mechanical systems. So we will be getting electromechanical systems that will be discussed inshallah in the later lectures. But in today's class we will learn about a translational mechanical system and its transfer function. Basically there are two types of mechanical systems. Let me show you. One is known as translational, and the other one is known as actually rotational. That will be discussed inshallah in the coming classes. Rotational, translational motion is that motion which is in straight line. This motion mechanical system, or this translational motional actually is that motion or that mechanical system or that mechanical energy or force that is inserted, or you can say the motion of the body after the application of force is in straight line. But rotational is that mechanical system which is actually moving in the circular path, or you can say in a curved path. So this is actually rotational system. This system we will be discussing this kind of system in the coming classes, but in today's class we will be looking at the translational mechanical system. That what is translational mechanical system? I just told you that this is the system which forces the body to move in a straight line actually. So thus this kind of system is known as translational mechanical system. We will look at different examples of translational mechanical system. We will also learn about the transfer function mechanism, that how we can find a transfer function of a given translational mechanical system. And similarly in the electrical networks we discussed about the first order circuit and the second order circuit. So we will also be learning about transfer function of one equation of motion and transfer function of 2 degrees of freedom. This term we will discuss this term in the later slides today inshallah. This is known as, normally you will be learning about this as DOF. It is mentioned in several books like this. DOF is basically degree of freedom. We will discuss that what is degree of freedom in the coming slides. Moving swiftly on, translational mechanical system transfer functions, you can see the diagram over here. There are three major components in any mechanical system. One is spring, another one is a damper, and the last one is mass. These three are the basic fundamentals or components used in a mechanical system, and this is the equations that you have learned already in your previous semesters in the courses of BMT, etc. Basic mechanical technology. You have learned about vectors as well as in the previous classes as well. So I will be revising you these topics in very brief, but it will be clear to you very much, inshallah. I will try my best to make you or explain you these topics. So there is a combination between force and velocity. You know that what is the combination between force and velocity? Force is basically the product of some constant k multiplied with the integration of velocity. So this is basically one equation that you will be using in your course. And this is also another equation, that is force into displacement. So F is equal to kx. This equation you normally have heard in the spring, that k is the spring constant, at x is the displacement that is covered by the spring. You see the spring, this spring is actually the constant of this elasticity, or the spring constant is basically k. And due to this force F, this force F, uh, you can easily find this value F force if you know the spring constant k, and you know that how much displacement the spring has covered. So if you multiply the k with this displacement, you can easily find the force. So this is the major equation that you will be using in your numericals, inshallah. F is equal to kx. Similarly, you can also find the impedance, and impedance can be found out by dividing f of s on x of s. So you know that f of x is basically uh, k into, you know that f of s is equal to k into x, k into x. Similarly, if you divide f by x, or divide x on both hand side, so you will be getting f by x is equal to only k. So you can see that f by x is normally known as k by using this equation. Similarly, the another component that is used in mechanical system is viscous damper. You can also see that there is a force applied outside and the body has covered some distance, but it is some kind of, you can say, resisting forces, damping forces. So you can also find these as Ft is equal to Fv, that is the force that is applied on the, as a damper, the frictional force, or you can say the resisting force is Fv, and it is equal F of total force will be equal to this small force multiplied with the derivative of displacement. So you can find this force, you can find this force actually by using multiplying this with the derivative of x of s. Similarly, there is a third function, that is the mass. So the equation, you know that F is equal to ma, for as the second equation of motion, F is equal to ma, and you know that a is nothing but the derivative of the velocity. So this is equation from this side, and if you put the value of Vt as you know that Vt is basically displacement of rate of change of displacement, so it becomes double derivative of x of t. You see that double derivative of x of t. So if you multiply the double derivative of the displacement with the mass, actually you can get the force. So here is the third equation, and you know that using this s terms, you can easily convert this d by dt into single s, and here is basically the square of d by dt. So you can easily put s square rather than just s. Now let us see the analogy between the electric networks and the mechanical networks. You can see that in electrical networks there were three components. One was R, L and C. Similarly, there are three components in the mechanical system, three basic fundamentals, that is mass, spring and damper. So you see that the analogy between these two electric and mechanical components will be used in very much of the electromechanical systems actually. But sticking with today's plan, we will be looking at only this translational motion, actually translation mechanical system. But this analogy I've just shown you because it should be in your mind that like mechanical system can be represented with as compared to the electrical system. You can see that in this diagram there is also uh, one S, no S, and sorry, S square. This is S square. You can see that there is no derivative, there is single derivative, and there is double derivative. Similarly, you can see that there is no derivative, there is no derivative, there is single derivative, and there is double derivative. So these is the basically analogies between electrical networks and mechanical systems. So starting with the first mechanical example, you can see that it is given that it has been asked to find the transfer function for this system. Actually, this is mechanical system, and it is asked to find the transfer function, and there is K, that is the spring constant, this is the mass M, and this is the damping force Fv, and this is your total force that you have applied, and this is the displacement that is covered by the mass. So you can easily find the transfer function by the same mechanism we will look at in the next slide, inshallah. Here is the detailed derivation for the transfer function. In this slide it has shown us the answer as well. This is your answer, this is your transfer function. But how you can find this transfer function, you can easily find it using this slide. So let's consider this diagram. You see that there is this is mentioned in time domain. The question was given in time domain, so I have converted this time domain into frequency domain, or you can say S domain. F of t becomes f of s, x of t becomes s of s, k of x of t becomes k of x of s, f of derivative of x become fs into x of s. Similarly, m double derivative of x becomes ms square into x of s. So basically I have converted the same thing that we did in the electrical networks. The first step was converting the time domain systems into time domain variables and time domain signals into frequency domain. The same process we are doing over here. We are converting the time domain variables and equations into S domain. So we did the same over here. Now we have to write the equation for this system. So you know that this is the total force applied, and this is the all the forces that are reacting towards it. So using you can know you know that the KVL or the KCL, if you remember, the total voltage rise is equal to the voltage drop. Similarly, the case is over here. The small forces that are acting over here will be the sum of the total force that is acting over here. So all the sum of these forces will be the actually will be equal to this f of t. So you see that f of t is equal to the force on the mass, the force on the damper, and the force on the spring. These three forces will result into the total force, that is f of t. So we have written this formula, this 2.108 equation over here. Now if you take the Laplace of this equation, you can get this term, that is double derivative become s square, single derivative become s, and there is no derivative, so it is represented as it is. So now you take x of s common from these terms. So inside there will be ms square plus fes plus k, and it will be multiplied with x of s and this f of s will be coming right away over here. So now you will solve for x of s divided by x of f of s. So if you divide x of s by f of s, you get 1 divided by ms square plus fes plus k. So this is your transfer function, which is mentioned over here. You see that this is mentioned over here. If you divide output to the input, you get 1 divided by this term. So there is another example for the translational mechanical system. This is very unique idea because in the electrical networks we did the first order equation and the second order equation. Similarly, we did some numericals on mesh analysis. There were two loops. Similarly, there is the same case over here. We are given with two masses, so the force will be 2. You see that one force will be of one damping force be of this mass, one damping force be of this mass. So there are 3 springs, 1, 2 and 3. So there will be 3 forces for the spring, 3 forces for the spring, 3 forces for the damping, 2 will be displacements, and 1 will be the total force. So this is very unique example, and they have asked to find the value of a transfer function, that is x2 of s, that is the displacement of this mass divided by the force that we have applied on the first mass. So basically this is the displacement of this mass is your output, and the force that you are inserting on the first mass is your input. So this is a very good example to understand the basics of translational mechanical systems. And you see that we have named it as 2 degree of freedom because we are dealing with two different bodies, and there is a direct combination between these two bodies that will help us to move the second body with the help of force that we are applying on the first body. So we are applying on the first body, we are applying the force on the first body, and we will make the second body move at cover some displacement x2 of s. So this is your 2 degree of freedom. Now let's divide this example, this huge example, into small portions. The first portion that will be coming will be of mass 1. If you see the mass 1, there is if you see the mass 1, actually you can find that there are several forces that are acting on the mass 1. One is the force that is inserting inside the mass m1. The second force is due to spring k1. Another force is because of the damping of this mass, and another force of is that the motion of that mass, the force that is applied on this mass, the F is equal to ma. This is over here. So these are the four forcing that is acting from this side. Similarly, this m1 is connected to another body with another spring, so it is because of this. Similarly, there is another damping between these two masses, and it. So now we will be solving this. You know that if we the mass is basically connected between different portions, different components. So you see that there are different components that are involved in between these masses. So we will be using the superposition theorem that we have already discussed in electrical networks, that if you are using there is a common component between two sources, you can or two loops, actually you can share them and you have to add them. Similarly, we will doing the same case over here. So if we hold m2 and still move m1 to the right, we see the forces as shown in this figure, that is here. So in this case, in this diagram, we have fixed a and we have fixed m2 and we are moving m1 to the right. Similarly, if you hold m1 and move m2 to the right, this m2 to the right, so m1 the force will be on m1 will be like this. This is the case where you have held M2 actually, where you have hold M2 actually. So you hold M2 and you move M1 here, and if you move hold M1, so let's see the solution over here. You can see that and the M1 and M2 have different components within between themselves. You can see that there are several components that are in between M1 and M2. And if you remember in the electrical networks, when we were discussing about mesh network, there was a common component R1 or R2 in between two loops, so we were sharing it on both hand sides. These components carry the effect of both the elements, the loop 1 and the loop 2. Similarly, these components will be carrying the effect of both of these masses. So let's say if we hold M2 and move M1 to the right, if we hold this M2 and move M1 to the right, this will be the forces that will be acting on M1. This diagram that is shown over here, this will be the forces that will be acting on M1. But if we hold M1 and move M2 to the right, let's say if we have held M1 and we are moving M2 to the right, these forces will be acting on M1. So the total forces that are acting on M1 will be the sum of both of these cases, that is this case and this case. So you can easily add these both because you know that there are different forces acting on the same body. So the total effect will be the sum of those individuals. So you can see that this is actually the spring which is applied from this side. Let me show to it very clearly. I have to draw the diagram, this diagram. It will be very clear to you, inshallah. So now you see that from this side, if you're holding M2 and you are moving M1 to the right, actually this side, so you are getting these forces that are acting on the M1, that is force due to the spring, damping force due to the mass, the force that you are applying inside, and the mass of the F is equal to m, the force of the mass by itself, which is in the reverse direction, and these two forces will be along the reverse path. So you can see that the total is equal to the sum of all these will be equal to, sum of all these components will be equal to F1 actually at equilibrium position or equilibrium condition. You know that about KVL, that sum of voltage rise is equal to sum of voltage drop. Similarly, the case is over here. If you add all of these terms, this will be equal to F of S if you want M1 to be at equilibrium, that is static position or uniform motion. Similarly, if you are holding M1, if you hold M1 and move M2 to the right, so these are the forces that will be acting on M1 and that will be in reverse direction, and this K2 of X will be because of this spring, and this damping force will be because of this damper. So now if we add all of these terms, you see that the total force on M1 will be the sum of these plus this. So you see that this k1 of x and k2x1 of s will be summed together in the first line. Similarly, this F damping force along with this damping force, they are on the same direction. You can see that they are on the same direction. So this will be in the second line. There is only one force over here, so this will be written as it is. And this is the mass, the force of the mass by itself, so it is the only one mass, so it will be as it is. And the remaining portion, that is k2 of x, that is mentioned over here, and fv of s of x of 2 will be as it is. So this is the total force on m1 in both the condition, if you are handling m1 or if you are handling at 2 m2. So this is this diagram is showing all the forces. You can see that this includes all the forces on m1 at any point. Similarly, you can find another portion, another forces on mass m2. So if you apply the held m2, m1 actually, and move m2 to the right, so these will be the forces that will be occurring on m2. And if you hold m2 and move m1 to the right, so these will be the forces that you will be getting on m2. Now if you sum both of these, you will be getting this equation. I hope you are practicing this with yourself. I have already suggested you to keep practicing these equations. I have done it for you in this first case. Now I expect you to perform the second case as well by your own, so that you will see that how can you solve the equations and the mechanical systems in future as well. So now if you are done with both the equations, you just have to write the equations. So in the first this diagram, you can see that there is only a one force, and that will be equal to one, this f of s, this one single f of s is in one direction, and these all are in the other direction. So f of s will be the sum of all of these terms that is remaining. So f of s will be the sum of all of these terms remaining. But you see a minus sign over here, and this minus sign is because these terms are actually in the same direction of fs. So this plus this plus this will be the equal to this plus this plus this. Let me give it a proper number so that you can understand it well. This 1, 2 and 3, this will be on one side over here, and all the remaining 3, that is let's say 4, this is let's say 5, and that let's say this is 6, this will be on this side. So if you want to calculate fs, you have to move these 2, 3 on this side, and this will cause it to the minus sign. That is the reason you can see the minus sign over here. You can see the minus sign over here. Similarly, you can write the equation for the second term, and you can see the minus sign over here. And by doing so, you are solving these equations. Actually, you have got two equations for your mechanical system, and using by the same Kramer rule, you can find the value of x2 of s actually. So using the same Kramer rule, you can find the value of x2 of s, and you have to divide that x2 of s onto f of s. And now the procedure is very simple. You have to write down this whole equation in terms of matrices, and then you have to apply Kramer rule, and you have to replace this f of s with the second column of the first matrix that will be coming over here. I hope you have learned that electrical systems in very much detail, so it will be very much easy for you now to apply Kramer rule over here. You can find the value of the delta, the same delta that we have discussed in the electrical network, that is the matrix, the original determinant of the original matrix. So if you have found the delta and you have found the x2 of s, you can easily divide x2 of s by f of s, and you will easily find the transfer function. In the next slide you can see that you find the transfer function. This is the transfer function. You can see that if you take this system and someone asks you to find the transfer function of this system, and he asks you that the output of the system is x2 of s, the displacement of the second mass, and the input is basically the force on the first mass. So you can easily find the transfer function using these two slides actually, and the transfer function comes out to be this equation, and this delta is actually representing the derivative, the determinant of the big matrix, the first matrix. You have to find that by yourself, and it will be interesting for you as well to learn these uh, basic mathematical rules. So that's all for today. I hope that you have learned quite a lot, and I suggest you to practice at least these equations in the coming 2 or 3, because you have the weekend uh, within the before the next class. So I suggest you to use this similar question for your practice as well. And if you have learned this question before, that you will be able to solve another questions. But if you are facing some problems, let's write it down, and do ask me in the coming class. I will be using paper for the derivation in the coming class, so you can easily ask me to ask me that, sir, kindly drive this equation for me or solve this equation for me. I will definitely solve for you, but for now I am giving you this as a task, because this is nothing but a simple mathematics, and you have done it already. I have described you the mechanism of the Cramer rules, the value of delta in the electrical networks. So I suggest you to practice yourself at least once before asking me. It is not difficult for me to solve it, but I want you to try it, so that it's more authentic and you will be learning more. That's all for today. I will see you in the class, inshallah. If you have any questions, kindly write it down. And if you are not able in the coming classes, you are not available for the coming classes, please mail your questions or put your questions or confusions or queries on the portal or on my email. I will be answering to you, as there is no problem. I see you in the class, inshallah. Thank you. Allah Hafiz.